The next topic is the charging system. The charging system replenishes energy expended from the battery to crank the engine on electric start units and may power a variety of accessories in varying applications. Electromagnetic induction is the basis of the operation of the charging system. Windings are arranged around posts on the stator. Magnets are affixed around the inside of the flywheel, which surrounds the stator. Magnets are installed with like poles adjacent to one another. The construction of the stator is such that the adjacent north poles align with alternating stator posts. The remaining posts align with the adjacent magnetic south poles. The result is a flow of magnetic flux from north poles through the stator core, returning to the south poles. Because the flow of flux is inward on one pole, outward on the next, and so on around the stator, the direction of the stator windings alternates between clockwise and counterclockwise between all pairs of posts. In this way, the flux is flowing in the same direction relative to the direction of the conductor, inducing a strong current in the conductor. As the flywheel rotates and the magnetic poles align with the next post, the direction of the magnetic flux flow reverses. This reverses the direction of the induced current in the stator winding. The result is an alternating current, one direction, then the other, repeating constantly as the flywheel rotates. If the output voltage were traced on a graph, the result would be a wave, with voltage alternating between full positive to full negative, relative to the movement of the magnets past the stator. Depending on the output of the system, stators are wound with different numbers of posts, varying numbers and size of conductor turns on each post, and different numbers of magnets. The greater the number and size of conductors and magnets, the greater the output capacity. Stators designed for special applications are also used on some engines. Separate charging and lighting stators may be wound on the same core. Some applications use a stator with no battery, such as the 4-amp unregulated system. The system only supplies current to operate an electric PTO clutch. Another special stator application is the braking stator, used on some lawn tractors. To bring the engine and cutting blades to a stop in accordance with safety standards, the tractor interlock system sends the braking stator circuit to ground at the same time the ignition is cut off. The added load of the braking stator reduces the coasting time of the engine and blades if the operator leaves the seat. The current required to charge the battery and operate most accessories is direct current, which always flows in the same direction. A means must be incorporated to convert the alternating stator output into direct current, which is usable by the electrical system. This means is the rectifier. A rectifier uses diodes to accomplish this task. A diode is a sort of electrical check valve with a closed circuit in one direction allowing current flow. The diode creates an open in the circuit in the opposite direction, preventing reverse current flow. A simple half-wave rectifier uses one diode to convert the output to just positive voltage, for example. The output would be positive voltage pulses. Because the circuit is open in the opposite direction, no negative current is induced, so a gap results between positive pulses. To make use of the full output potential, a full-wave rectifier is used. 4 diodes are arranged to form an electrical bridge between ground on one side and the battery positive post on the other. In the center of this bridge are the stator output leads. When a positive voltage pulse arrives from the stator, current flow enters one side of the bridge and is blocked toward the ground side of the bridge, but is allowed to flow to the battery. Current flows through the battery to the ground side of the bridge. It re-enters the bridge and is allowed return flow to the opposite end of the stator while being blocked from the battery. When the induced current reverses and a negative pulse is exposed to the bridge, it enters the opposite side of the bridge. Here, the same blocking to ground with forward flow to the battery occurs. The circuit is completed through the bridge ground connection to the opposite end of the stator. The rectifier converts the alternating current into a continuous stream of positive voltage pulses, which is used by the electrical system. Alternator stator output must be controlled in some fashion to provide adequate charging while preventing overcharging and battery damage. In some cases, this is accomplished by matching the construction and output of the charging stator to the total requirement of all the electrical loads on the equipment. When no other accessories are used, this method of charging circuit control is quite simple and reliable. In higher output systems, this type of system would not be sufficient to control the charging output and provide stable system voltage. A solid-state electronic regulator is used to control charging system output. Solid-state electronic components monitor battery voltage and compare it to stator output voltage. Internal switching controls charging output. In a simplified explanation, a voltage sensing circuit controls a solid-state switch. The solid-state switch acts as both a half-wave rectifier and a switch. When the battery voltage is low, the solid-state switch is closed and the charging circuit through the battery and stator is functioning. As the battery state reaches full charge, the sensing circuit sends a signal to open the solid-state switch, opening the charging circuit and regulating voltage to a specified level. Charging system tests, like ignition tests, have some common steps regardless of system. Test the battery for ability to accept and hold a charge. Charge the battery fully before testing the charging system. A voltage test is performed to determine if the charging system is capable of developing voltage sufficient to charge the battery. The values observed in this test will vary from one system to another, depending on system regulation. Begin by attaching a voltmeter across the battery. Before starting the engine, battery voltage should be approximately 12.2 to 12.8 volts. If not, charge the battery before further testing. Start the engine. With the engine running at 3600 RPM, the voltage should increase to 13.8 to 14.7 volts within a few minutes of starting. If the voltage is above 14.7, the system is overcharging. Test the rectifier regulator as explained later in this video. If the voltage is to specification, apply a minimum 5 amp load by turning on headlights, electric clutch, or other load. If a load is not available on the equipment, connect a 2.5 ohm 100 watt resistor across the battery terminals. When the load is applied, the voltage should remain in the specified range. If the system does not maintain the minimum voltage, the system is not functioning properly. Start the engine and run it at 3600 RPM. Remove the connector from the rectifier regulator and insert an AC voltmeter across the outer connector sockets. The open circuit stator output voltage should be at least 28 volts. If the open circuit stator voltage is above 28 volts, the rectifier regulator should be tested, as explained later in this video. If the stator output voltage is below 28 volts, test the stator resistance. Stop the engine and check resistance across the two outside sockets, which should read from 0.06 to 0.2 ohms. Replace the stator if resistance is out of the specified range. Check the resistance from one lead to ground. The resistance must be infinite. If the resistance reading is very low, the stator is shorted to ground and must be replaced.